Today, let's take a look at an old problem in mathematics. Why are there infinitely many primes? To start, we need to figure out what a prime number is. By definition, a natural number n greater than 1 is prime if it is not divisible by any natural number other than 1 and n. For example, 7 is prime because it is not divisible by 2, 3, 4, 5, or 6. However, 4 is not prime because it is divisible by 2. Now let's take a look at an equivalent definition, which will be more useful for proving the result that there are infinitely many primes. Here's our original definition. We say that n greater than 1 is prime if it's not divisible by any natural number other than 1 and n. But instead of the condition that is not divisible by any natural number, we change this condition that it is not divisible by any prime number less than n. Now you may be asking, why are these two definitions equivalent? Well, here's why. Any prime number by definition 1 is a prime number by definition 2. Because if a natural number is not divisible by any natural number other than 1 and n, then of course it won't be divisible by any prime number less than n, because these prime numbers are a subset of natural numbers other than 1 and n. And the second requirement we need to show that these two definitions are equivalent is that any composite number, which is a number that's not prime, by definition 1, is a composite number by definition 2. Let's take a look at an example to show why this is true. 60 is divisible by 30, and by definition 1, 60 is not a prime number. But here's why this also works for definition 2. Let's take the number 30. Since 30 is not a prime number, we can break this down into a product of two numbers, and both these numbers are not equal to 1 or 30. So here we choose 2 times 15. Now let's see, 2 is a prime number, so we leave it alone, but 15 is not a prime number, so we break 15 into a product of two numbers not equal to 1, so we have 2 times 3 times 5. Therefore, any composite number, we can eventually break it down into a product of all primes. And now we can say that 60 is divisible by 2, 3, and 5. Therefore, 60 is composite by definition 2. Now that we know the definition of a prime number, let's prove the result that there are infinitely many primes using a boring formal proof. I don't know what these things are, but they do not look very happy. You don't like boring formal proofs? Do it our way or suffer? Well, okay, fine. Let's instead do an elegant proof to show that there are infinitely many primes. Oh wow, these things are back, but at least they're happy now. Here's how this proof will work. I will come up with an algorithm to generate the primes one at a time, and I will prove that this algorithm will never terminate. Therefore, there are infinitely many primes. Here's the definition of a prime number in the top right corner, just for reference. Now, suppose I have an infinite number line, and on every single natural number, I have a lighthouse that is unlit. On 0, I have a lighthouse which is evil. This lighthouse wants to destroy every other lighthouse that is not a prime number, and it wants to light up all the lighthouses that are prime numbers. Since 1 is not a prime number by definition, let's destroy this lighthouse right away. Here's how this algorithm will work. The evil lighthouse will choose the first lighthouse that has not been destroyed and has not been lit. Then, the evil lighthouse will shine a light of that wavelength. For example, the first lighthouse that has not been lit is lighthouse 2. This lighthouse is obviously a prime number because it is not divisible by any number less than 2. So the evil lighthouse will choose to light up this lighthouse because it knows it's a prime number. Then the light will continue to oscillate and hit all lighthouses that are a multiple of 2 because the light has a wavelength of 2. Then all these other lighthouses will be destroyed because we know those are not prime numbers, since those lighthouses are divisible by 2. And now the evil lighthouse repeats the process. 3 is the first lighthouse that is not lit and not destroyed. It will shine a light of wavelength 3, which will first hit lighthouse 3, we know that 3 is a prime number because its lighthouse has not been destroyed by any of the previous prime lighthouses. Now the evil lighthouse lights up the first lighthouse it touches, then destroys all other lighthouses. Next, lighthouse 5 is the first lighthouse that has not been destroyed or lit. The evil lighthouse will shine a light of wavelength 5. We know that 5 is a prime number since it has not been destroyed by any of the previous lighthouses. Now, lighthouse 5 will be lit up. All the multiples of 5, which are not on screen, will be destroyed because those are all divisible by 5 and therefore they are not prime. And this algorithm continues with lighthouse 7 and 11, and so on, but those are not on screen, so we won't show those. Now let's answer the question, does this process repeat infinitely? This process stops if all lighthouses are lit or destroyed. We know that if this process repeats infinitely, that means there are infinitely many primes, because at each step of the process, we light up one lighthouse on the coordinate of a prime number. So if we prove that this process repeats infinitely, that means we proved that there are infinitely many prime numbers. Let's suppose that this process has happened a finite amount of times, and we will show that there is still at least one lighthouse that is not lit or destroyed. Let's say the lighthouses lit by this process are P1 all the way to Pn, and these are listed in increasing order. So P1 is 2, P2 is 3, P3 is 5, and so on. Now consider the number P1 times P2 times P3 all the way to Pn plus 1. This product plus 1 is greater than Pn because it is the product of Pn and other numbers plus 1. Since it's greater than the greatest element of the list, this lighthouse is not lit. We also know that the product plus 1 is not divisible by P1, P2, P3, all the way to Pn. Here's why. Let's try dividing this product plus 1 by any element of the list. Let's call this pk. This is going to equal the product divided by pk, which is simply the product with pk missing. So that product divided by pk will be an integer. And we have plus 1 over pk. 1 over pk is not an integer because pk is a natural number greater than 1. Therefore, this is an integer plus a non-integer, and it is a non-integer. Therefore, this product plus 1 cannot be divisible by any element of the list. This means that the product plus 1's lighthouse is not destroyed. And this means that when we apply this process finitely amount of times, there will always be a lighthouse that is not lit or destroyed. Therefore, this process will repeat infinitely. This means that there are infinitely many primes.